So this is optical monitoring of dust environment around lunar exploration sites. Authors are Lolachi, Glendar, and Stubbs, and Ramin will be presenting the talk.
Can everybody see my screen okay? See the slides?
I see a black screen. It says you started sharing, but double click to enter full screen mode.
Oh, right, I'll try just a sec. I'll try it again. Apologies. Okay, anything now?
Same thing.
Same thing. All right, just a sec. My apologies about this, folks.
Any advice from Mike Tollin if you're on?
All right, I assume you can see your desktop now at least.
Yeah.
Okay, and then if I do that, can you see the slideshow now?
Nice.
Yes.
Yes.
Okay, sorry about that, folks.
Looks good.
Okay, so with Artemis, we have a new era of human lunar surface exploration coming. The Apollo program showed us that dust is a nuisance and a hazard, being abrasive and potentially toxic to human health. So it would be a good idea for us to be able to monitor it. So to that end, we created models of dust light scattering behavior and distribution for irregularly ellipsoid and spherically shaped dust grains, as shown on the right. The grid covers UV to near infrared wavelengths and grain sizes from 0.01 to 100 microns. Modeling irregular grains is important as most real lunar dust grains are not mesospheres, as shown in the inset electron micrographs on the right and from other people's talks today. And we use discrete dipole analysis at small grain sizes and the Hapke equivalent slab with Allen diffraction at larger sizes because of the computational expense of DDA at larger sizes. We then coupled this with a simple dust dynamics model we created to simulate dust raised by activities like astronaut, rover motion, in situ resource utilization and the like. And then we combined all of that in a radiative transfer model to model the brightness of sunlight scattered by an exploration dust cloud caused by these activities. This was basically to answer the question, could you build a camera with off-the-shelf parts with flight heritage as an exploration site dust monitor? And the answer to that seems to be yes. So we can now show a preview of some of the grid scattering properties. On the left, you'll see the scattering coefficient over different size regimes indicated by line steel for irregular grains. The sampled effective grain radii range from 0.05 to 50 microns. Differences in scattering coefficient due to grain size can be observed. Absorption increases dramatically at short wavelengths, so scattering is less and is dominated by the diffraction component. For comparison, we now add lines for the other grain shapes that we tested, prolate spheres in orange and spheres in blue. Differences in scattering coefficient due to grain shape can be observed. Now we present a sample of the normalized scattering phase function over different size regimes, again indicated by line style, and this is for 530 nanometers in the green. The plot shows the dust grain shapes results for irregular prolate spheres and spheres, where the colors are as for them on the left-hand side. It can be seen that smaller scattering angles are a good diagnostic of size, whereas larger angles constrain shape. Larger radiances can be seen at small scattering angles, but this is too close to the sun for a camera really to be practical. From the plots on the right side, on the right-hand side, differences in phase function due to grain size and shape can be observed. There's also variation in wavelength, but this isn't shown for the sake of brevity. We validated our grid against measurements of JSC 1A lunar simulants scattering, where they measured scattering properties by Escobar Cerezo et al. In 2018, and we found that there was a good agreement between our grid and their measurements. So in order to simulate the sensitivity of a notional commercial off-the-shelf COTS hardware camera, we need to model just spatial distribution and abundance across an exploration site, such as a lunar surface space. We created a simple trajectory model for dust launched by activities such as ISRU, astronauts walking on the surface or robot wheels. This uses a Gaussian velocity distribution in accordance with the exploration activities just mentioned, and we set the most probable speed of that velocity distribution to 2 meters per second. This would be for a steady state dust cloud generated by activity at an exploration site, rather than the short-lived instantaneous high density clouds created by these processes. This is analogous to the permanent tenuous impact-generated exosphere seen by Harani et al. 2015's results with using LADI, and represents what astronauts would be exposed to on a chronic rather than acute basis. The figure on the left shows our size distribution governed by the power law seen on the right, which is controlled by the exponent alpha. For the purposes of this study, we assumed a baseline value of alpha equals 0.91, which is consistent with the measurements of Harani et al. 2015 and the lunar ejecta cloud. But to see the effects of changing the size distribution, we varied it between 0.8 and 0.99, which are the blue and the orange curves. So using this dust dynamics model, we created spatial dust distribution of dust with a peak value of 1 microgram per cubed at the origin. This mass concentration scales as Gaussian exponentials in the vertical and horizontal directions from the peak value, with vertical scale lengths of 1.2 meter and a horizontal scale length of about 100 meters. The resulting distribution you can see in the figure. On the left is a cross-section of the mass concentration model across the exploration site, and on the right is where we zoom in to see how the model will be experienced locally. We give the astronaut, surveyor lander, and Apollo lunar module silhouettes for size comparison to the vertical scale of the dust model. Because of the large difference between the vertical and horizontal scale lengths, astronauts and spacecraft would locally experience an almost plane parallel change in dust abundances. Combining all of the previous elements with the radiative transfer model, we simulated sunlight scattered by dust grains at an exploration site. We could then compare the model dust radiances to the detection thresholds of nominal dust monitoring cameras created with off-the-shelf hardware. So here's a sample of our results. Imagine a camera facing the sun that is scanning in elevation above it. The sun is at 4 degrees above the horizon, indicated by the pink sun symbol on the elevation axis. The figure shows the broadband signal to noise, SNR, for the path integrated dust line of sight, varying with elevation angle, using a conceptual camera using the LiSEA-Q PL1 image sensor and a 1-second integration. This is for our baseline scenario using a regular grain with alpha equals 0.91. SNR is shown for the dust model path integrated case, is the black line, and the case with dust increased by a factor of 10, black dashed line. The thick dashed gray line represents a 3 sigma measurement above which dust is confidently detected and adequate for constraining the dust size distribution. You can see a good fraction of the SNR lines are above the detection threshold, indicating confident detection. To see the effect of changing alpha, the coefficient controlling the size distribution power law, we add equivalent lines for alpha equals 0.8 and 0.99, as indicated by color. Large differences can easily be seen for different values of alpha, so a camera should be able to constrain size distribution pretty well. For comparison, we now add green lines showing the SNR from zodiacal light for a camera placed either at the poles of the equator. The zodiacal light is a potential source of interference, but also a possible calibration source. So on the right, we start off with the same figure as we did for the case on the left with the regular grains and alpha 0.91 and the 3 segment detection threshold, but this time the idea is to look at the effects of shape. So we add the blue and the orange lines, which indicate results for different grain shapes, prolate spheres and spheres, and finally we add zodiacal light again. So although we can see some differences between shapes, shape distinctions more subtle than it was for size distribution, and more information on shape would be obtained if polarization was also measured. In addition to the LiSEA-Q PL1 image sensor results that we showed, we also tested notional cameras using a Saimiya sensor used in booster cameras and a Hamamatsu CCD, which also gave positive results. So in conclusion, what we've found out, site dust characterization should be achievable using automated simple swivel off-the-shelf camera hardware, even for a highly tenuous exploration dust cloud. Dust abundance and effective grain size are readily measurable with such a camera. Calibration could be achieved using the periodic response using zodiacal light, and current and future work is based on extending the DDA functions of the grid to larger sizes and also including geometric optics. This will allow for the inclusion of polarization effects, which will then allow us to constrain shape as well, better than without using polarization, and we have a manuscript in progress. So with that, I'd like to thank you very much and ask if you have any questions.
Yeah, thank you, Ramin. I think my timer glitched out, so you are perfect with how you timed everything. Does anyone have any questions for Ramin?
I have a quick question. Ramin, in one of your early slides, you showed a slope for dust detectability by grain size. And it looked like the 3 slopes that you showed, it was very hard to discern different grain sizes in the less than, say, 10 micron or less than 1 micron grain size. Is that correct?
Is there which one? Which plot was that you were talking about?
Oh, it was very early on. It was like
oh, okay, just for
grain size versus, yeah, that one.
Okay, this one. Okay, so sorry, what's the question?
Oh, so the question is, how well can you deter, because most of the dust will probably be in the less than 10 micron grain size, and even more, it might be in less than 1 micron. How well are you able to discern those different grain size into fractions?
It seems to, yeah, so it seems to come out pretty, you can see that there's larger differences, but basically as you get, the thing is that once you get up to about 50 microns here, the reason that they're all the same is essentially because we're switching from the DDA over to the Hapke equivalent slab. So they're basically all giving the same results. And there's sort of an interpolation between about 0.5 microns, which is the end of the DDA grid, and 10 microns, which is the beginning of the Hapke equivalent slab. So the thing is that there'll probably be more differences at the larger grain sizes than are available here. But until we can basically switch out the stuff at larger grain sizes, we won't be able to tell exactly how big an effect that has, because this is essentially a kludge until we can finish, until we can basically extend the grain size in a better, extend the grid in a better fashion at larger sizes.
Okay, cool, thank you.